There, I'll start the recording, and I can't wish you a happy garbage day today because it wasn't garbage day in my neighborhood because of the
Oh,
holiday
did it
yesterday.
get postponed any day?
Yeah, half my neighborhood did not realize that though, so their cans are sitting outside, but we knew that. We'd look it up. So yes, I'm all messed up this week. It's not garbage day, but we are going to persevere because I have in front of us one of my favorite things to teach, interaction terms. Yay. So I am not done yet with example 5. It is a monster, but it's the last one. So I have one more model to put in it, and then I will be done. I'm excited to tell you that Jonathan fixed the p-values. They are no longer in scientific notation.
Ooh.
So I got it fixed. I'm very excited
Tell him
about that.
thank you from us.
Yes. And it's one of those things, it's like, I know this has to be an easy fix, I just don't have the right words for it. And he's just like, oh, that's a such and such. I'm like, can you come put that in my program? And he did, so it's nice. Even people who are teaching the class need to know when to ask for help. Am I right? Mm-hmm. So don't ever feel bad that you feel like you should know something and that you shouldn't need help. Just get the help that you need. It will go better. So we are talking about moderation in this unit. It is a very common type of research question. These types of models show up in every walk of life. So I think it's something that I want you to be able to be familiar with and use in future work as well. So a list of things with it. Starting off, this is what we're talking about. 2 predictor variables being multiplied together to make a new thing. So in the notation, same as we usually have, y sub I, what's that? What's y sub I? What does that mean?
That's the actual value.
The actual value
of your piece of data that you're trying to predict.
Yeah, the outcome variable, you were going to say? Or
Subvariable.
yes, and yeah, the variable that we are predicting as an outcome, that's in this notation scheme, it varies across individuals. That's what the sub I means. Beta 0 is still my fixed intercept. Beta 1 and beta 2 and beta 3 are fixed slopes. None of these betas have i's because they're fixed. They're constants. They are not variables. X is a variable, Z is a variable, and the 2 multiplied together, this thing is called an interaction term. And you can think of this as adjusting the dial for how strong the effect of each of these predictors is. So what's going to happen is that the effect of Z is going to vary as a function of where you are on X. The effect of X is going to vary as a function of where you are on Z. So we're going to end up creating different slopes for different folks.
Cool.
Yeah, it is really cool. So the idea of moderation, usually a research question is phrased as like a predictor and a moderator. So for instance, if I have something like, does stress harm your health more if you have this characteristic? Like if you're a member of, let's say, a minority group, is stress more impactful for you? Or if you are an elementary school teacher, is stress more impactful than if you're a high school teacher? Something like that. In that kind of question, the predictor would be stress, and the moderator would be the grouping variable, because it's like 4 different kinds of people is the moderation idea. But that depends entirely on how you're thinking about it. It is not a mathematical distinction. So it is equally correct to think about X as the moderator and talk about the effect of Z for different kinds of X's as it is to go the other way around. Interactions can always be evaluated, no matter what kind of predictor variable you have. However, this is where the language and history of general linear models gets a little bit tricky. So if you learned analysis of variance, that is the term. That means you have a quantitative outcome being predicted by one or more categorical predictors, and you're interested in mean differences across your quantitative outcome. In those models, by default, if you have like 2 different grouping dimensions, interactions are included always. If you have a very complex ANOVA type design, let's say that you have 5 dimensions, something like a 2 by 2 by 2 by 2 by 2, you would have up to a 5-way interaction estimated by default in the software for you. It's just baked into this language. And there's usually no trimming of the model. People leave in things that are non-significant and interpret the things that are significant. In contrast, in ANCOVA, That's when you're adding a quantitative predictor known as a covariate, that's the C part. You are told that you can't have interaction terms of your covariate with the other dimensions because it violates the homogeneity of regression assumption. Well, that seems awfully arbitrary. And it turns out you can. You can put interactions in, you just can't call it ANCOVA anymore. Then it's just a standard linear model. In regression, as it is typically known, that is when we have quantitative predictors of a quantitative outcome, then nothing happens by default unless you tell it to. So there's no default interactions at all. And in most standard regression software, you literally have to create the multiplicative variable yourself. Like you'd have to build a new column in your data set that is x times z. Fortunately, in the code that we are going to be using, we don't have to do that in most cases. So we're going to do it within the code. And you've actually already seen this. For quadratics, remember we had age times age?
The I.
So that type of technology is what we can use to do interaction terms. So we have a lot of new vocabulary that goes with this idea. Fixed slopes are now going to be of different kinds. So you will hear me switch my terminology accordingly to talk about main effects. A main effect is what I would call beta 1 or beta 2 in this analysis because it's of one of the predictors all by itself. So main effect versus interaction. Interaction is when they're together. The rules are, if you have an interaction term in your model, then you have to keep the main effects with it. Otherwise, it doesn't have the right interpretation. So even if the main effect of x is non-significant, if you want to keep the x by z interaction in, it stays. It's the same premise as when you have a quadratic slope, you have to keep the linear slope with it. So if you have x squared, you need to have x underneath it, or x squared doesn't have the right interpretation. The role of an interaction, though, is something that is tricky to understand at first, but I promise you that it's like one of those magic eye posters. Are those still a thing? They're like constellations of dots, and if you stare at it, like a 3D image kind of pops out. Once you see the image, you can't unsee it. I feel like this material is a lot like that. Like once it clicks, it will be there. It takes effort to get the clicking in. Ironically, I can't see the magic eye posters. I've never actually seen one. Yeah, I don't know what it is. I don't have it. But hopefully everyone else does. So the connection is that we're going to talk about the interaction term not as what it does to y. We're going to talk about it as how it affects the slopes. And then the slopes affect y. So there's like a downhill progression here. The idea of a main effect slope no longer applies in these models. We have to talk about what happens to the slope as a function of where the interacting predictor is at 0. So this is a different kind of taxonomy than we're used to, or excuse me, a different kind of conditionality. So I built a taxonomy about this. So here's the terminology. In most models, fixed effects are either going to be an intercept or a slope. An intercept gives you the expected outcome when your predictors are 0. A slope tells you what the difference is in the outcome for a 1-unit difference in each predictor. Cool. Slopes then now can be called 3 different things in terms of how you think about them. And the labels I'm using for this are bivariate marginal, that's one idea, unique marginal, the second idea, and unique conditional. And the rules are as follows. If you only have one fixed slope in your model, that slope's main effect would be considered bivariate, meaning just the 2 variables at a time, and marginal, because it applies to everyone. Like if I told you the slope of x is 2, then everyone's outcome goes up by 2 as a function of where you are in x. It's not a different slope for each different kind of person. So marginal means like unconditional, it's for everybody. If you have more than one fixed slope, so in the examples that we've seen recently, we have multiple predictors in the model. So it's no longer bivariate, because now the predictors are fighting against each other for common variance. They each want to get their unique contribution. So we're switching from the label bivariate to unique. Whether it's marginal or not depends on whether the predictor is part of an interaction term. If it's not, it's marginal, and the slope applies equally to everyone. If it is part of an interaction term, then it is unique. It is conditional, and so this is the new part. Unique is the term that I prefer for this, but after controlling for, after adjusting for, conditioning on, all of those terms mean unique. Unfortunately, the idea of conditional is most often referred to as something called a simple slope or a simple main effect. And they're not trying to be mean, but it kind of comes off that way. The irony of that label is that this is one of the more complex topics that I have to talk about. There's nothing simple about it, but that's the terminology that people use, for better or worse. So these are the general principles. Let me walk you through some examples to make this a little more concrete. So this lecture series, by the way, I'm going to do a lot of typing in, and I will post the finished version when I am all done so that you have that. So let's say this is my model right here. The slope of W as my predictor variable as it relates to Y. Now, would I call that bivariate marginal, unique marginal, or unique conditional? What do you think this one would be called?
First one.
We got vote for the first one. So there's only 2 variables in the problem. So I think bivariate works for that. And this slope beta 1 applies equally to everyone because there's nothing in the model that would say otherwise. So I'm going to call this one bivariate marginal. Now let's go to the next model. Now the effect of W is the unique effect after controlling for X, Z, and their interaction. So now what's the label? 2?
Unique. Yeah, unique.
Unique. Yep. Now, is it marginal or conditional? And the answer to that is it an interaction term?
Marginal.
Yeah, W is not part of an interaction term. So therefore, beta 1 is the slope of W for everyone, and I would call this unique and marginal. Now, how about X? Slope of X. And Zoomers, you can play too. I'm watching the chat. Or you can talk. Your call. Beta 2. Yeah, unique conditional is the vote. I'll write down the unique part. And what got you to that answer?
Well, the conditional because the X is part of the interaction term.
Yep, X is part of the interaction term. So beta 2 is not the only thing in the model that says what the effect of X is. To know what the effect of X is, we have to know what Z is. So that implies that the effect of X, this beta 2, is specific to when the interaction term would drop out when Z is 0. So it is unique and conditional, and I'm going to put that in parentheses on Z equals 0, because that is the situation in which beta 2 would be the sole source of a slope for X. Okay, with me so far? Now how about the slope of Z, beta 3? What do I call that?
Unique marginal.
Marginal.
I heard unique,
Marginal.
and I heard marginal, and I heard conditional.
Conditional.
Okay.
Conditional.
And I'm still hearing both.
Part of
50-50 shot, yeah. So in this case, Z is part of the interaction, so it's the mirror image of what X was. It is unique conditional, but
On X equals 0.
on X equals 0, exactly.
So I'm not able to understand why are we saying 0, Z equals 0 or X equals 0.
Because if, let's do the X first. So if I'm concerned about the effect of X, and I want to know what the effect of X is for each person in the sample, I have to know what their Z value is to know that. And if Z is 0, this entire term drops out, and all that's left is the beta 2 controlling the slope of X.
X, okay.
And so that means the interpretation of beta 2 here is that it's conditional. This is the slope of X only if Z is 0.
Correct, yeah.
Otherwise, it's going to be this and this put together in a linear combination, which you already know how to do. Believe it or not. So then the other one works the same way. Beta 3 is the slope of Z exclusively only if this goes away, which would happen if X is 0 instead. So these are both unique conditional. Last one, the interaction term, beta 4. That is a fixed slope for the multiplicative combination of X and Z.
conditional, but no z or x equal to 0?
Is that conditional then?
It is.
It's marginal. It is because,
Ooh.
think of it this way.
Okay.
X times z is like a new idea. Is that idea mentioned anywhere else in another term? Nope. So beta 4 is the interaction term for everyone. It is marginal.
Oh, okay. Can you have 3, like an x, a z, and a q
Yeah, you
that are
can.
multiplied?
Yep.
I'm
You
not
can
saying
have
we
three-way
want to do
interactions.
that. I'm saying, yes.
I'm not going to do that in this class.
No, that's okay.
But
Just in general
yes,
curiosity.
yes, you can go up to whatever order of interaction that you want. The only catch is that you have to have all of the lower order pieces. So if you had a three-way interaction of 3 different variables, then that implies 3 two-way interactions underneath it and 3 main effects, each variable by itself.
So you grow exponentially.
Yes, it gets complicated. So the reason that I'm trying to give you labels for these things is because these map onto different ideas. Bivariate marginal means this is the effect of one variable on another without controlling for anything, just like straight up. And the effect applies to everyone equally. Unique is the idea of what does W bring to the table that X and Z don't? What is its unique combination after controlling for whatever overlap it has with the other predictors? But because there's no interaction terms, then this slope for W applies equally for everyone. It's marginal. Up to this point, we've only had these 2 possibilities. It's the third one that this unit is introducing, the idea of conditional. Because conditional doesn't just mean controlling for the other stuff in the model. That's what unique means. Conditional means, no, it's more specific than that. It's not just controlling for, it's specific to the interacting predictor being 0. Specific to, not just controlling for. So that means that if you have a research question about the importance of X and the slope of X is non-significant, you might be inclined to say, well, X doesn't matter. But that's not right, because X doesn't matter if Z is 0. It could start mattering if Z is 2 or 4 or 8 or whatever. So each of these slopes changes as a function of the interacting variable. Okay, how are we doing so far? I know it's new. We're going to spend some time on this question, or just thinking. We're running a thumb label.
Yeah.
How are the thumbs today? Can we get a thumb check? Sideways, I'm hoping for sideways. That's what I'm hoping for. Oh, we got a few up. Okay, good. The good news is that this gets fairly straightforward if you can learn the 4 kinds of interactions. There's only 4. And guess what? You already learned this because that's the same kind of quadratics. An interaction term takes each of its main effect slopes and it takes it and makes it more positive or less positive or more negative or less negative. That's it. You figure out what quadrant you're in and you're good to go. If the answer is more anything, that is known as an over-additive interaction. That means that the effect is becoming stronger as a function of the moderator variable. If the answer has less in it, that's an under-additive interaction and it is becoming weaker. So up to this point, we've only had additive. The multiplicative combination changes it to over or under additive. So let's play. Here's my model. Okay? W is now irrelevant.
Okay.
So let's say that beta 2, right here, is 10. That would say then that for every 1 unit increase in X, Y goes up by 10 if Z is 0. If the interaction term then is a positive 2, which quadrant am I in terms of what the interaction is doing? Top. Yeah, which set of words? More positive, less positive, more negative, or less negative?
More positive.
This is a more positive. So what is going to happen is that the effect of X is 10 if Z is 0. If Z goes up by 1 unit, the slope changes from 10 to 12. And if Z goes up by 2 units, the slope changes from 10 to 14. The slope changes, not y, the slope. That's the key. If you talk about the interaction term as what happens to y, you will get confused. Its job is to change these main effect slopes, which then trickle down to y. Now this one, next box. Slope of x is still 10. So if z is 0, for every 1 unit increase in x, y goes up by 10. Interaction term now is negative. So they're working against each other. Which one is this? This is less positive. Can't type. There we go. So if z changes from 0 to 1, what's my new slope of x? 8. And if z changes from 0 to 2, what's my new slope of x? 6. So is x still, let me back up. Does x still have a positive slope in those examples?
It starts positive.
Yeah, it starts positive at 10, and then it goes to 8, then it goes to 6, then it goes to 4. Yeah, it's still positive, but it's less positive. And eventually, what's going to happen?
Negative.
Yeah, if it'll keep going down by 2, it'll flip to negative. So if z is like 100, then we have a negative slope for x instead.
Z could be negative. and
Z
then it
could be
goes up.
negative, and then the slope goes up again. Yeah,
But then if you think about the graph, it's still overall less positive.
yes. I once had a student argue with me because of this, that less positive and more negative were the same thing because they're heading the same way on the number line. Look at your x. And my response to that was, tell that to the Weather Channel. I don't know if you remember this, but it's the language is still in your apps, but there used to be a television station called the Weather Channel, and they would have like the local on the 8s, where every like the 8 of the hour, so like at like 1:08 and then like 1:16, like all that kind of thing, they would play the weather. And if it were in the summertime, your choices were hotter or not as hot. It was never cooler. And in the winter, it was cold or not as cold. Like not as cold is like less negative or less positive, not as hot. It's still hot, to be clear, just not as hot. So I'm taking this from the Weather Channel. Now what about this one? Yeah, if x has a slope of negative 10, now that's the disco version. As x goes up, y goes down. And then the interaction term is negative, it's going to kick in and make it more negative. Yep. So x has a stronger negative effect as z goes up. Now that could be a good thing or a bad thing, depending on what your outcome is.
Less negative.
Yeah, the last one is not the remaining one here, less negative. So the mores, these are making your effect of x stronger as a function of z. You're moving the slope further away from 0 in either direction. The lesses are doing the opposite. They are moving the slope towards 0 in either direction, and they're therefore making the effect smaller. Now you can get out your GRE vocabulary words for a lot of these things because there are many synonyms that you can use for things like less positive and less negative. The effect of x is exacerbated by z. The effect of x is diminished by z. The effect of x is mitigated by z. There's a lot of words that you can put on this to convey this idea. And I have had to do that in papers because people are like, what the hell does less negative mean? The answer is it's dampening effect. That's the, okay, let's talk about, let's see. You want to do stories or you want to talk about centering? Make it a choice.
Stories.
I made some stories. I put them on the website
Please.
because I knew I wasn't going to get example 5 done in time, and I still wanted to have some, something besides X, Y, and W to talk about. Okay, I've got some stories. These are example research questions that would involve moderation. So I want us to go through these, try to figure out, like, conceptually what the equation would look like, and what direction you think the coefficients would go to be consistent with these hypotheses.
Okay.
Okay, so the first one was brought to me by a student during the pandemic.
Cool.
Hypothesis was camera use on Zoom is related to better course grades, but less so in larger classes.
So grades is going to have a fixed
Yeah, so
slope.
if we start off my
Perfect.
equation here, and I'm not gonna use notation, I'm just gonna type. So I've got a beta 0, right?
Yeah, good.
Can I just do B,
Sure.
because I'm lazy?
Yeah.
I'm going out of room.
I'm lazy too. I like it.
All right. So then I need a main effect, as it is called, for each of the variables in the problem. So camera use would be one, like that. What's the other one?
Class size.
Yeah, class size of some kind. And then we would have the interaction term, which would have both. Camera size. Okay. I'm going to copy that, put it down here. Now, what direction do you think these things would need to go? And keep in mind that the main effects are conditional on wherever 0 is for the other variable. So do you think that people who turn on their cameras get better grades? Looking at the Zoomers for this one.
Question. Is camera use in reference to you or in reference to the student?
The students.
Because that makes a big difference
Yes.
as an instructor.
Yeah, it's intended to be, the context is like a Zoom class.
So if I,
And
as a student,
it's whether the students are choosing
attended,
to turn their cameras on.
my camera's on.
Yes. Do you think that camera use is related to grades?
I think so.
Yeah, if it's a proxy for engagement.
Yes.
If it's a proxy for engagement, then
or
perhaps.
knowledge, reading the student to see do you understand or not.
But if you have a student who doesn't have their camera on and it's because their room is a mess and they don't want everyone to see literally their dirty laundry, they may still be engaged but have a very valid reason to not put the camera on. So, but if we're willing to say that it is indicative of engagement, then I would put a positive slope here. So I'm going to put P for positive. What about class size? Do you think that's related to grades?
I think
Could
yes.
Yeah.
Say yes. Which
Yeah.
way does it go? Are larger classes have better grades
Negative.
or worse grades?
I think
No,
it goes down.
Lesser grades.
Lesser.
larger class, fourth grade.
Okay, larger class, worse grade, and this would be specifically in people who don't have their cameras on, if camera use is dichotomous here. Now the interaction term. Camera use on Zoom is related to better course grades, but less so in larger classes. Which pattern is this? Is this a more positive, less positive, more negative, or less negative?
Less positive.
Think is it less positive? Yeah, so
Diminishing?
camera use is related to grades, but less so in larger classes. So to make that work, the interaction term would need to be positive or negative.
Good question.
If we want to make the slope for camera use weaker,
Less positive.
yeah, this needs to be a negative so that, you make that bolder so we can see it, so that it is undoing the positive effect of the camera. The positive slope would be reduced in larger classes.
This is only if you're fixing the size of the class, correct? Or are we fixing the camera?
What do you mean by fixing?
So in other words, like before we had, like when x was 0 and z was 0, okay, that meant we were talking in terms of a particular slope changing or not. And
Yes.
so when you're doing this, we're talking about just only impacting our B1 value of slope.
So this effective camera is specific to whenever size is 0.
Right.
So let's say that I centered size such that it's the average class size at the
Okay.
university. Okay, so it's a meaningful reference point. So in average size classes, there's a positive effect of camera use. As class size increases, we would want to have a less positive effect of camera use. and it would require a negative coefficient to bring that back down. Does that make sense?
Mhm.
What do we think? Does it feel okay? Or not okay? Should I draw? Okay, getting out paint again. I don't have a cool iPad pencil thing, but I have paint. All right, so we have camera use, essentially. C for camera.
Mhm.
Here's my 0.
And
Here's
then
my
you get a
1. Okay, it's only 2 kinds. So we think that there is a positive slope of camera use. So let's say this is a small class, this is a medium class, and this is a large class, say. Small, that's an S. Medium,
And
large. There. Do you know how hard it is to write with a mouse like this?
Yes.
You should see me sign my name on Adobe things with the mouse. It looks like a toddler's scribbled on it, but it's authentic. So the idea would be that camera use has a positive effect, but less so in larger classes. It's less positive. So eventually these positive slopes would switch into the negative direction according to this. So if you're staring at a Zoom screen with 300 people, it probably matters less that you have your camera on for your engagement / grades in your class than if you have a class of 5 people. It's more obvious. That was the idea anyway. These are just examples. Okay. Want to do another one?
Sure.
Why not?
Yeah.
Hypothesis is that persons who are receiving a new treatment relative to an old treatment decline less over time in health than people receiving the old treatment. So think of this as a context of preventing further disability or disease.
We start with B0.
Yep, B0, got that one. So then
Sorry.
we would have beta 1 for whether they are in new or old.
So that would be dichotomous also, like we do with the camera?
Yep, we can do dichotomous. Decline less over time. What's my other predictor in the story?
Time.
Time.
Mhm.
Age.
Time or age? Yeah, we're going to go with time since that's the way that it's worded in here. And yeah, you can do that. That's the class before this one. That's what longitudinal analysis is about. I stole it from that class. Filled with crossovers. So time. Then we need my interaction term of new and time. Okay, let's figure out the pattern. Let's say that time 0 is the beginning. And let's say that we randomized people into whether they got the new treatment or the old treatment.
Mhm.
Should there be a group difference if that is the case at time 0?
Yes.
If I randomize
Oh,
people
wait.
and time, we haven't really started doing anything to them yet?
No.
Like if 0 was before we intervened in any way?
Yeah.
Yeah, I would think that this slope would be 0. Or it should be if random assignment help. And the story says that we're expecting decline over time. So that implies that, like, if you do nothing, this is what's going to happen.
Mhm.
So let's make that one negative.
Okay.
And in order for the group getting the treatment to decline less, what does this one have to be?
Positive.
Positive. And what makes you say that?
Because the time is growing, the time is passing by.
Well, yeah, time is going on. So as, like, if you think of the x-axis as time, people are going down.
But they're not going down as fast with the new treatment.
Hopefully they're not going down as fast, and so that would require a positive interaction term to work against the negative slope here. So maybe people in the old treatment decline by 10 units per year. People in the new treatment only decline by 7 units per year. That would be accomplished through a positive interaction term counteracting the negative slope. So this would be a less negative example, whereas the first one is less positive. Do I need to get paint out for that? Would that help? Maybe not.
Yes.
Yes, okay. Thank you for being emphatic. Okay, new drawing. Now this is T for time. So let's say this is the old treatment. They're declining over time. Boo-hoo. And let's say the new people look like that. They're declining too, but not as much. So there's no main effective group at the beginning of time, but there is going to be one, hopefully, by the end. So that's why I made a point of saying time
Randomize
zero,
and-
because you need to know where time zero is to know what the main effective group is. If you centered time backwards, like people do that you can put 0 here, in which case like this would be -1, -2, and so forth, then you would expect a group difference, but not at the beginning. How about, this is an example from a friend of mine's dissertation many years ago, a buffering hypothesis. That's another terminology people use for these models. Stronger tendencies towards forgiveness relate to a reduced impact of stress on disease severity.
Got it.
Beta 0.
Beta 0.
Beta 0, hey, we know we got that one.
now.
Yeah.
All right, what are the variables in my story here?
Forgiveness.
Forgiveness, yep.
And that's dichotomous also? 'Cause
Nope, this is a scale.
Oh, it's a scale.
It's a scale.
Oh, this is a scaled effect.
Yep, it's going to be a measure of individual differences that I helped create, the Heartland Forgiveness Scale.
Yeah, so question about dichotomous. What does that mean?
Binary.
Binary.
Okay.
Binary is two choices that are 0 and 1.
0 and 1.
Dichotomous is two choices, not necessarily 0 and 1.
Okay.
So you are using it like a multi-categorical then? Or
No, like this would be like the sum of your responses to 18 questions about how forgiving you are.
Okay. I'm trying to picture your question that you asked to get your.
Like it would be something like, I tend to hold grudges, and then it's like not at all true, a little bit true, mostly true, completely true, something like that.
And then you just
I like
compile,
it.
and you compiled it together.
And you compile it, and we pretend it's interval. That's right.
Okay, thank you.
And measured perfectly. But that's a
Yay.
different class. So we have forgiveness in the story. What else do we have in the story? Stress. Okay.
And diseases.
And so disease severity is going to be the outcome in that case.
Oh, sorry.
Yep. No, but you're right.
We
It's
have an
in the story.
interaction that we want to attempt to see if there's.
Yeah, you got to know the variables in the problem. And let's say stress is also a scale score of some kind. So these
Okay.
are continuous variables, or quantitative variables rather. All right. Do you think forgiveness helps disease severity?
Yes.
Sure. Why not? So does it make it worse or make it better?
It makes it better.
Better.
Less severe.
So it's negative.
This is a negative. It's like the golf example.
Mm-hmm.
Oh.
I know, but
I know.
There are-
Yes.
Back and I was like, no,
Yes.
golf scores are good.
Yeah.
low golf scores are good, just like low disease severity is good, and low poverty is good, and low criminal rates are good. There's a lot of outcomes that you want to go down.
Mm-hmm.
I stand by it. I know it's golf, but I stand by it. So yes, if being forgiving is helpful, then you should have, that means that people who are higher in forgiveness should be lower in disease severity.
Mm-hmm.
Is stress helpful or harmful?
Harmful, but it's positive because making it go up.
Yeah, so it's harmful, but we have a positive effect. And this is where the English part of it gets tricky, because when you say positive effect, you mean the sign or like it's good for you?
In terms of whatever your variable is.
Yeah, so this is a positive slope that is creating a bad thing.
It's logic, unfortunately.
I know,
You get it.
but it's easy
Yeah,
to get
yeah, yeah,
confused.
yeah, yeah.
So then we've got a negative effect of forgiveness, a positive effect of stress, and the idea is that stress, let me back up. The idea is that forgiveness buffers the effect of stress. It makes it less harmful. So what does this need to be for that to be true?
So,
Less.
You want to make it less?
makes it less
Less for sure.
negative, but it's bad.
Well, this is a positive slope of stress
Right.
because more stress is more severity.
Right, so it's less negative, even though the severity is going up, but we're measuring it going up. So
If
it's
we
okay.
stick with just the sign and not the
Right.
intent,
Right.
so it can't be less negative because this is positive to start with. So the question is like, this is positive or negative, then
Oh, I
does
thought
it
we
get
were
more or
gonna have
less?
to change our,
Yeah, so this is the predictor and forgiveness is the moderator.
oh, sorry,
No, no worries.
makes a difference.
Zoomers say less positive,
I
so
would
how do we
agree
make
with
it less
that.
positive? This is a negative sign.
Mhm.
Yep. So they're working against each other.
As long as we know who the moderator is.
I'm sorry?
That's it, as long as we know who our moderator is.
Well, and this is the thing, is that this question is worded to imply that forgiveness is the moderator. We're studying the effect of stress on disease severity in different kinds of people. That's the idea here. The other version of it would be we're studying the effect of forgiveness on disease severity in people with different levels of stress. That's the other way to word it. And I'll tell you what, beta 3 don't care.
No.
Math don't care. Beta 3 is going to answer both of those questions simultaneously. It's up to you to tell the story in the way that is the most aligned with what you want to know. Last one. This is a little bit tricky. Diminishing returns as an idea. Spending more time rehearsing stops improving performance and might even hurt at some point.
Yay, beta 0.
Beta 0 for the win. Performance is the outcome.
Well, you need time,
Yeah, practice time or something like that.
practice time, rehearsal time, whatever you want to call it.
Yep. I'll put practice in here. Are there other variables in the problem that I don't have in my model yet?
Performance.
Performance is my outcome.
Time.
Practice time is what this is one of these. So you're thinking like, well, I don't see another one, but this is in the interaction example, so there must be some kind of
Is it possible
interaction.
to like
Yeah.
a squared term?
Hey! It
like,
is.
like a parabola shape? Yeah, like an upside down parabola, so you get
Yeah.
it up and then that's something.
There's my interaction term. You already learned how to do this.
Yay.
Quadratics are interactions. So I can make it.
Interacting with itself, so to speak.
Yep. So practice helps, right? To a point.
Mhm.
So probably positive. How do I introduce the idea of diminishing returns? Stops helping. Negative. Yep. That would create a slope that goes up, slows down, and eventually tips over.
Cool.
Cool. So just a few examples, but you will start to see these a lot in the literature once you look for it, these kinds of buffering ideas or mitigation ideas. There's another word at the top of my head, and I can't come up with it. Hang on, give me 1 second. Like, oh, I'm so close. It's something to do with risk.
Risk analysis. No?
Yeah, something along those lines, like risk factors for things, essentially. Moderators that make effects stronger are risk factors. That's another piece of language people would use for these things. So, 4 choices. More positive, less positive, more negative, or less negative. Start with the direction of the sign, and then see if the interaction is working with it or against it. If they're opposite in sign, it's less positive or less negative, and then the effect is getting weaker as the moderator goes up. If they're the same in sign, the effect is getting stronger as the moderator goes up. Let's talk about centering.
Oh boy.
You already know how to do this too. What does centering mean?
Shifting to 0.
changing the definition of 0 by shifting the scale, usually by subtracting a constant, but if you had a range of a variable that was all negative numbers, you might have to add a constant to get to 0 instead. And this is the point in most books where they would introduce centering for the first time, because this is where it truly starts to matter. Up until now, the only consequence of not centering your variables would be having a weird intercept that can't happen if 0 isn't within the scale. But that is no longer true because of the conditionality of these things. So let's say in my story here, Y is student GPA on a percentage scale out of 100. X is parent attitudes about the importance of education measured on a 1 to 5 ordinal scale. How important is this to you? And Z is parent education level measured in years of education. And so my model has example numbers in here. I have a main effect of attitudes. So this is the new terminology. When you have interaction terms, the slope of the variable all by itself is called a main effect. I have the main effect of education, and I have their interaction term. And let's say these are the results that I got. So these variables are uncentered. This is how they are measured as described up here. So beta 0 is my expected outcome. It is GPA for what kind of person?
No attitude and no education.
Yeah, attitudes equals 0,
Sorry.
which cannot happen.
That's true. Oh.
And education equals 0, which theoretically could happen but is very unlikely. Okay, but that's why it's so low, right? 30 is a very low GPA. That's because we're talking about someone who doesn't exist. Who cares? It's just the intercept. Let's move on. All right, beta 1. Beta 1 is the slope of attitudes. So I would say this is the change in Y per unit at. Am I done typing, or do I need to keep going?
Do you have to mention the being conditional?
I have to add the conditionality. For
education equals 0?
For education equals 0, because that is the point where this would be the only thing that creates a slope of attitude, because that would drop out. So this is the importance of attitudes for people who never went to school. So we are 0 for 2 with interpretable parameters so far.
Yes.
Not a good sign.
100%.
How about beta 2, change in Y per unit ed for
Attitude 0.
attitudes equals 0, which cannot happen. We are 0 for 3 for interpreting.
We're batting 100 or 1,000.
Yeah, we're batting 0 for interpretable parameters.
Okay.
Now the interaction term. Which pattern is this? If I talk about attitude as the moderator and I'm focusing on the slope of education. The interaction term is 0.5, the slope of education is 2. So the interaction term is taking the education slope and doing what to it? Increasing it, and it was positive to begin with.
More positive.
This is a more positive. So we got the pattern right. Now the question is, how do we talk about this 0.5?
That's the rate of increase as education increases by 1?
Close.
Okay.
So the trick to this is to not start the sentence with change in Y. The trick to this is to start the sentence with change in beta 2.
Yes. Yes.
What happens to beta 2 per unit at? That's how we do it. The slope of education increases by 0.5 per unit attitudes. The slope does, not Y, the slope. If we go the other way and focus on the slope of attitudes being moderated by education, then it would be the reverse. Change in beta 1 per unit. Oh, darn it, I did it backwards. Oh, yep, no, I got it right.
You got it right.
I got it right. There we go. Okay. Now, is the interaction term conditional? Do I need to say anything further? Like specific to this value being 0 or any of that? What do we think? May I ask the question another way? Do you see any other term in this model that has both things at the same time?
No, so
Nope.
it's a unique marginal.
It's
but-
marginal. That means that this beta 3 is for everyone. The interaction term is unconditional. That means that it will not change as a function of centering. But I can figure out from this model predicted levels of GPA for any kind of person. That's not going to stop me. The fact that 3 of my parameters are not really interpretable does not invalidate the model. It's still okay. I'll still get the same R-square, the same predictions. So if I want to figure out what's a predicted value for a reasonable person, let's say middle of the road attitudes of 3 and high school degree, 12 years of education, I would put that into my equation. So 30 is my fixed intercept. We know that. 1 is the slope of attitudes. I put a 3 in the parenthesis there for the value of the variable I'm filling it in. 2 is the slope of education. I put a 12 in the parenthesis for that. And then 0.5 is the interaction term. I put in each of the predictors that go with that. If I do the math on that, that works out to be 75.
Let's see.
Okay. How are we doing? Now, are you dissatisfied with 3 of the parameters being meaningless? Because I am. Yeah, he's like, it's fine.
Sorry, that's the math in me. It's a 0, it's a number.
Well, here's the situation. If
But
you,
in practicality, I'm not happy with it.
yeah, like the problem and why I think this is so important is that it's very easy to forget the conditionality. Like if you get this result and you're like, oh, that slope's non-significant, I guess attitudes don't matter. No, attitudes don't matter in people who never went to school, but the model says they're gonna start mattering as education increases.
Mm-hmm.
So it's very tempting to look at these slopes and be like, that's the story of this variable, but it's not. So for that reason, I find it dissatisfying, because you're more likely to miss the interpretation. But-
So I have a question about.
Yes, please.
I'm sorry.
Yeah, no, go ahead.
How did we get 1, 2, and 0.5?
They're fictitious numbers that are easy to work together in my example.
Okay.
There's no other reason than that.
So we can think about our numbers on our own.
We
That's right.
will get, like, if this is what the output said,
Okay.
then this is how we would interpret it.
Right.
I'm just making up numbers.
Got it. All right.
So are we assuming, I get that attitude can't be 0 because our scale is measured from 1 to 5.
Right, attitudes cannot be 0.
In our sample, I guess, are we assuming that years of education is like high school is the lowest that we have?
This is, I meant it literally in years, so like 12 would be 12 high school degree. So 0 would be no education at all.
Why is that wrong though?
It's not necessarily wrong, but it's unlikely, I think, that in a research sample about the importance of education and attitudes that you would have someone who has no schooling whatsoever. If you had a different kind of sample in which that was a possibility, then leaving education uncentered to refer to those individuals would be a reasonable thing to do. So it's a combination of like, what is the possible range of the variable in the first place, and then where are your people? Like ideally you want the 0 point to be where people are in your sample, and it has to be possible. Possible at a minimum where people are as a desirable property.
So you could technically say, I want to start at, they have a college education, and that could be your 0.
Yeah, so you could change that.
If that's your
yeah.
study.
Yeah, and that's what we're going to do to fix it, is we're going to center these. So here is a new version of the model in which I centered education at 3, and I centered attitudes at 3 and education at 12.
Mm-hmm.
And I got new results.
Ooh.
Now, I know how I got there. Let's just pretend that you don't know and you don't care, and we'll just reinterpret this, and then I'll show you how I got these new numbers, okay? Now beta 0. Given the new centering, 75 is the expected GPA for what kind of person? For attitude is 3, because that's now where 0 is.
Education.
and education is 12. Okay, so where that came from, 75 is what I got when I plugged in those numbers into my model. So that's the first one. Now beta 1 is the change in y per unit at, that's the same, for what kind of person? Conditional on what? Previously it was ed equals 0, and now it's still ed equals 0, but 0 means something new. It's 12, yeah. So we're 2 for 2 in parameters that would mean something. Because now I can talk about the importance of attitudes in someone who has a high school degree, and that slope is now 7 instead of 1. Beta 2 then is the slope of education, so the change in y per unit ed for
Attitude 3.
attitudes of 3. Yep, you're catching on. 3 for 3. And that number used to be 2 and is now 3.5. The interaction term is the same number. It's unconditional. It is marginal. And it means the same thing. So for attitude as the moderator, what do I type here? I'm interpreting the effect of education specifically in people with different kinds of attitudes. Do I start with change in y?
No.
Correct. No. What do I type instead? Change in beta 2. Exactly. That is what the interaction term is doing. Per unit what? The change in the slope of attitude or education per unit attitude. Yep. It's the other one. And if I go the other way, change in, what do I say here?
1.
Beta 1, because now I'm talking about the slope of attitudes is a thing I care about in people with different kinds of education. So this is per unit ed. Yep. There we go. So you can see now why centering would matter. Your main effects could refer to impossible things. And that's not as helpful. Okay, questions? All right, then let me add to this just a little bit. We're going to review how to generate predicted outcomes, and then I'm going to show you how I got these new slopes. So this is code we get to fill in, pseudocode, as it were. Here's my model. This is the centered version. If I wanted to generate predicted outcomes for different kinds of people to make a picture, this is the longer manual way of doing it. There's shortcuts in code that you can use, but I want you to understand the principles, which is why I'm doing it this way on purpose. So this is Stata code. This is our code. These are lincoms, stands for linear combinations in Stata, and I'm using the glht function that allows us to make linear combinations out of fixed effects in R. So I'm telling you in the comments here in the labels what I'm trying to generate predictions for. The first one is a predicted outcome, a y hat, for somebody who has high attitudes of 5 and relatively high education of 16. The first thing that goes in is always the constant. Because nothing multiplies it, it will always contribute to someone's outcome. So we start there. So that's why I have constant times 1, and I have a 1 in the first multiplier spot in the R code. Now, you don't actually need to type this, right? Like there's no difference mathematically, just writing the constant versus times 1. I'm doing that for symmetry across the other packages, and it works the same way in SAS. You have to put a 1 somewhere. So the question then is, what do I put here if I want to generate a predicted outcome for somebody who has 5? And note the centering.
2?
I put 2 here because 2 is 2 more than 3. 5 is 2 more than 3. That means down in the R code, I would put a 2 there as well. If I want a prediction for someone with an education of 16, what goes here? 4. And here is 4 as well. Now, what goes in the interaction spot? 8, because 2 times 4 is 8. So I'll put 8. I didn't want you to make that smaller. There we go. 8. So this isn't so bad, right? We can do the other two. Attitude of 1, what goes here? Yeah, we're centering at 3, yep. -2. -2. If we are, okay, doesn't like that. There we go. I like them to be aligned. It makes it easier to read. I'm of that kind. Education of 9. -2 is because we're solving for attitude of 1, and attitude was centered at 3. So it's like I would say 1 minus 3, and then the result is -2. So we're plugging in the original value here, then we subtract 3 from it to get the centered version. So if I want an original value of, we're doing education of 9, what do I put?
-3.
-3, yep. And what goes here?
-5.
6?
So yeah, -6.
No,
Minus
6.
plus 6.
Plus 6.
Okay.
2 minuses. What do I put here?
Minus plus.
This is -2 here and -3 here. So the multiplier together, it's 6.
6.
Yeah, I think you were adding instead of
I get
multiplying.
it.
Yep. Easy mistake to make. And that one down here would be 6 as well. Okay, last one. Attitude of 3. What goes here?
0.
Yeah.
Yeah, no attitude.
And education of 20.
8.
-2 of 8.
8. Very good. And then what goes here?
0.
0. Yeah. So finish that out down here.
Oh, at least I got that done.
Okay. So this is not so bad, right? Predicted outcomes?
Yep.
The next trick then is predicted slopes.
Oh boy.
Same logic, and I will teach you that next time, but that is how I got from this version of the model that's uncentered to the version that is using the centered predictors. It changes the main effects. I can do it quickly, and then I'll show you more algorithmically. If I wanted to solve for the slope if education is 12, then I start with 1, and I need to multiply 0.5 times 12. That gets me to 7. Likewise, if I start with 2, if attitudes is 0, and I want to know what it would be if attitudes were 3, I multiply 3 times 0.5 and add it to the 2. And then that gets me to
Makes sense.
the 3.5.
Yay.
Mhm.
Makes sense. Like it.
So in practice, if you're stuck with a main effect that doesn't mean anything, you can always ask for other ones and get unstuck from the same model. That's what we'll learn to do next time.
Thank you.
Yay.
Questions or anything you want to comment on before we adjourn for the day? Yes.
We'll update this class's contents in our website.
I will probably do it when we're all the way done filling things in,
Oh,
but if
okay.
you'd like me to do it sooner, I can do that.
Yes,
I can put up an
because-
intermediate version.
Because we need, especially for me, we need the contents to review the you just described.
Yes.
Yes.
Okay, yeah, I can put up this version and then we'll keep adding to it and I'll post like the finished version so there's when everything's all said and done.
But your video is going to be uploaded before the next lesson, right?
Yeah, the videos I usually put up later the same day.
Right.
Or the
okay,
next
these are-
morning.
Thank you.
Yeah,
Appreciate
no
it.
problem.
Very
Yeah, happy to
helpful.
do so. All
All
right,
right.
then how about 4 extra minutes of your life back today? I'm so
Yay.
generous, I
All right,
know.
thanks.
All right, let me know if you need anything. You have a formative assessment or homework? Yep, yes.
Formative assessment.
That's,
Formative.
yep, that's open. You can work on that. That's due Monday.
All right.
So, all right, see you Thursday, folks. Thanks for being here. Bye for now.